เอายังวะ Okay, so um, anyway, Happy New Year. Anyway, so well, we continue the topic on thermodynamics, right? Last time we finished about the second law of thermodynamics, right? I gave you a definition of the definition of the second law, right? At the beginning, we have a statement of impossibility, right? That is a keyword that I put there, and then later on we introduced a quantity that we call entropy, right? To capture that kind of impossible process, right? Okay. So today we continue on the topic thermodynamic potential. Okay. So, well, so far, the state of the system is, well, actually can be described by like these two pair variable, right? And then you can specify what is the state of your system, right? And so, but it's not necessarily, well, we have more than these two, right? We can define temperature, right? Internal energy, okay, and of course entropy, well, actually I would say that in this context we consider the change of the entropy. All right. So, okay. So you see that now we have kind of more than two variables to play with, right? We have P, V, T, U, and S now, right? So we have a set of variable. Actually, we can play with. So now next we're going to mix and match. That's what we're going to do, and then let's see what we could get, right? So first one, let's consider internal energy. Okay, U. So we know that actually from the first law, you have this relation right here. And suppose that, so this is your system, which is I give you a number number particle, okay, and the volume, and of course this internal energy, and this is outside is nothing but surrounding, right? Okay. So then, so you can turn this one into this, right? By using the definition of the chain of the thermodynamics entropy that that actually I did introduce previously in the previous class, and then this one can be put in this way, right? So now you have this relation. So it's, if this system if we left this system for a very long time, so it's going to get to the equilibrium, right? That is the thing. So it means that at that equilibrium, this all quantity will be constant right here. Okay, going to be constant. Do not change at all after it reaches the equilibrium. And of course, you can use this variable will completely specify the state of the system okay. Suppose that now you go, you're looking at the closed system. It means, well, I give you a definition what is a closed system, right? Okay. However, for open system, so let's put a closed system. Okay. There is exchange the particle between the particles between the system and the surrounding. Right. System surrounding. It means that then we must extend the first law right by adding this bit. I mean, this bit coming from the exchange of the particle, which is actually, this is called the mass action. Right. Which is describe the energetic genetic contribution of so I put here of material exchange. So it means that now it's like your system has a hole somehow, and then there is some exchange of the particle through this hole with the surrounding. But it's not necessary to have a hole here, but it means that what I mean is the boundary of the system can be I mean it's allow the system and the surrounding exchange the particle. That is the thing. Okay. So now, we write this quantity, this in terms of this mu dn. So this constant is called chemical potential. Right, which it actually depends on the type of the particle, right? Depend on type of particle. Okay. So it means that in general, we would have, we put this one, right? You may have different many type of particles that actually contain, right, has been confined in this system, and then it's going out or getting in your system. Okay. And so let me put a note here. So you may wonder what is kind of meaning of this physical potential, right? It must be because when you add this term into this equation, then you see that this is kind of work done. Somehow it means that this one might be need to explain more or less the same, right? With that quantity dw. So this going, so is defined as the energy needed to add particles to an isolated system. That's it, okay? well, to add or actually or taking out, right, take out or add in, okay. So it means that this term represents how difficulty your particle will be get in or get out. That is the meaning of this the whole thing. That's okay. Then sorry นะเดินเยอะหน่อยเดินไปเดินมาไหนบอกมึงอยู่นิ่งๆไม่ได้หรอ Okay, so let's look at this where for the simple case that actually we have only one type of particle in your system. So now it means that so your U is a function of these three variables right here. So because this the chain one, right, of that is the coefficient, but actually once we know that if we say that this U is a function of the three variables S, V, and N, it means that if you consider this du, then you're going to have this equation, right, which is very trivial. And then you have a look on this. The temperature can be defined in this way. It means that you fix these two variables, and then you consider the change of the U with respect to the this S entropy, then you get the temperature out. Similarly, if you would like to compute the pressure, you can use this, and of course this one as well, the chemical potential. Then you fix S and V, okay. Now I'm going to be calling the second law, right? The second law that we have this is the second law that we have, right? Okay. So from this inequality, we can write, let me finish this cleaning first. So from that, so you could add on the left hand side, you could add this, right, and then on this this side, you could do forget this one, okay. So it means that so this whole thing is nothing but this du. So you get this inequality What does it means by having this? I'm going to call is Hawkeye equation. So it means that this one, I mean this new equation is already covered this equation, right? Okay. So if you look at thermal equilibrium, right? This constant, right, when fixed, right, it means that there is no change of the three variables. So you get 0 here. So this implies that the change of the internal energy must be satisfy this inequality. Okay. This implies that the spontaneous process always lead to a reduction in the internal energy U. Sorry, my U is too cute. Okay. So what does it means by having this statement? Can you discuss a bit what I'm put there? This is quite an important bit. What does it mean? Yeah, let's discuss about this. What does it mean by this bit? Never what?
They never lost.
Never lost. Well, not really, because it's decreased, right? But it's I'm not sure what do you mean by never lost. But it is it can be transformed to another type of energy. But well, normally so like this system, right? If I put a chalk here, and then if I left it, it's going to fall down to the ground. Why is that? Do you know why is that? Why the chalk is falling down if I leave it? Because of what? Yeah, of course yeah, of course there's the gravity, but now we're talking about the potential in it. Yeah, and of course and decrease in what, and then what? No, well, yes, okay. So Okay, so it's, if we say that actually the cloud is the reference, so it means that here at this point you have higher potential, right? But the cloud you have a lower potential. It means that your system always prefer to be in the state that a minimum potential, right? Energy or something like that. That is another way that you can say that why the shock has to go down, because it prefer, yeah, the minimum energy to be the state of the minimum energy. And then of course there is the gravity that pulling down. Of course but the cost of the gravity pulling down, that it is pulling this shock into the lowest, the lower state of in energy. So that is the thing. Okay, so let me so this, you can say that this is the chain, right? Okay, so the system to minimize U, right, at fixed here, right, something like that. So your system will be drive to the state actually lower and lower energy, the lower and lower internal energy. That is the thing. Okay, hope you. I put this with the system will be somehow will be forced to a minimized state, okay, of this U at the fixed, okay. All right, so now we kind of finish the first quantity, the U, internal energy. The next one, we're going to look at entropy. So now, if we treat entropy as a quantity that we need to consider, right? Okay. Okay, so your S is going to be a function of U, V, and here. So now, we have okay. So why did it just here from this Gauss equation? I just move thing around, right? You will get this. And so, of course, that if you wish to put only the change of the entropy, so you will get this elation. And again, since this is a function of UVN, so it means that you can put right here. Right. And then you match again these two equations. Then it's not difficult to see that. So it's not difficult to see that. You will get this relation. If you fix this, and if you, okay, you will have this relation here. And if you look at this carefully, you just see that actually this and this is just reciprocal to each other. Right, simple as that. And anyway, so again, I'm going to click calling the second law. Okay. Okay, I do this again. And so you know that what is a dq, right? dq is a du plus and this one. Okay. So now you have a new inequality I call normal equation. So for the U, if you treat U as a potential energy, you have this inequality. But for this, you get this instant. And again, at equilibrium, okay. So this whole thing, I mean, no, not whole thing. The chain of these three quantity will be 0. It means that so the change, the entropy must be greater or equal to 0, which is again nothing but the second law itself, right? Yeah. So it means that the system will be forced again to maximize state of entropy. Okay, that is the thing. So the thing is that now you need to minimize U. The system always prefer to be in the lower energy state, right? But for if you treat if you look at the S, your system prefer to be in the state that higher entropy. Okay, that is the thing. Okay, next one. the third one. So enthalpy. So to define this very weird name of this new quantity, we start with the definition of the U. Okay. And so what I'm going to do is that, so I'm going to put 0 in there magically. I'm going to add this bit and take out this bit. Right. All right, here. So it means that, so what we have now is that this derivative of the product of the P and V, right? Okay, so then now I move I move this bit to the side. So then I'm going to define this as new quantity that called enthalpy, right? So it means that this enthalpy is a function of this T quantity, right? Again, so it's not difficult to see that. It's not difficult to see that we can find out that there is this relation here, right? Then you can compute the temperature from this condition. Okay. But in chemistry, you might have heard a lot of this quantity, right? Because chemists use a lot of this quantity to study the system or to see how the system evolve from one state to another state, right? But I understand that in chemistry they focus on the special case that they keep this pressure as a constant. All right, that is a thing. Okay. Okay. So again, I recall a second law. Okay. Then I do more or less the same trick. You can see that here we have TDS here, right? So then what I'm going to have, I'm not going to do it for you. I think you can do it yourself. You're going to have this inequality out. Okay. Okay. It means that for and spontaneous process drive the enthalpy to a minimum at fixed what SP and N. Okay, right. So it means that, so normally your system, again, if you choose to use this quantity as a potential, right? So it means that your system will be, again, prefer to be in the lower state of the enthalpy, like you do have for the internal energy. All right. Okay. Very good. Next, the next one. We have Helmholtz. Yes. Yeah, we have Helmholtz free energy here. Again, I start with this definition of the chain of internal energy. And what I'm going to do is that, so I'm going to add a magic zero again, but in different way. Okay. Yeah. So what you have and then I move this to this side. I'm going to have and then I shall call this F as a Helmholtz. It's such a difficult name. Helmholtz free energy. Okay, which is the function. Which is the function of T, V, and N, right? And again, so it's not difficult to see that your dF can be put in this way. Right. And then, so you compare between these two equations. So what you have is that you're going to have this F T. Very lazy guy. Minus F or V, yeah, actually. And T, no, actually not, cannot be T in, this should be the V, right? V, yeah, this is T, and this is mu, which is S and N, of course, and then this is going to be T and V. All right, so we have again this kind of relation, and again calling out a main player, which is the second law, again and again. So then you find out that once you apply this second law, you're going to have this relation. Again, this inequality, right? Okay, and then you in this case, I put a box here, so you have this inequality, which is then, so I don't want to put, you can say that actually for the spontaneous process, we drive your Helmholtz free energy to the minimum if you fix the same interpretation as we do have for the enthalpy and internal energy. Yeah, except one, entropy. This quantity is quite different. Okay, next. Okay, give free energy. So if we start from this definition, okay, and so again, do a magic trick by add 0 into this. Okay. So it means that you're going to have this one, and finally you could put things in this way, and you're going to call this quantity as a Gibbs free energy, yes. Energy, which is a function of the three variables, right? And of course that if you look at the chain of this, it's not difficult at all to find out this relation, and of course that Close that. You will find here. Okay. And again, take a law. Right. This second law will lead you to this inequality. Of course. Oh yeah, GP, right? Yeah, thank you. And you can say again, therefore the spontaneous process will drive your Gibbs free energy to the minimum, right? Okay, I think we are good. So the last one, I'm not sure. Yeah, it's the last one. What time is it? 10? ในเวลามันเดินช้าจังนึกว่า11:30แล้ว หยอก Okay, so this is the sixth one. Six, you have called gland potential. Okay, I'm going to use this notation. So in some textbook, we're going to use this one. Well, it doesn't matter. It's just agreement and what kind of thing that you're going to use. So again, you start with this. Yes. df here, mu dn. Okay. And again, I put a magic zero by at here. Okay. And so it turned out that actually at the end, so I skipped the math because, well, it's more or less the same trick that we did so far. Then you will get this here, which I'm going to call this as grand potential. Right, which is of course a function of these three variable, and is you consider the chain of this, so you get okay, this one. And. So what you're going to have is that here. And so the second law, again, will get you to this inequality okay. And again, it means that your system, for the spontaneous process, your system prefer in the minimum grand potential state, right? Okay. 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 Can I take 5 minute break? Okay, thank you. Okay. So let me summarize what we have so far in just one diagram. So this is summary. Okay. So here at the beginning we have this quantity u, right, as a function of the three variables, right? And so you could change this u to be a new quantity called f by add this term, right, and you will get f. Similarly, you could have this by add this bit, okay, and of course that, so you have this gives free energy, okay, by this, and then you have this. You see this structure is more or less is kind of the parallel to each other. It means that along this vertical direction, if you add this PV, you will get a new quantity. But on the horizontal direction, if you add this, you will get a new quantity. That's very interesting. However, we have more than 4, right? We have 6. So it means that you can do better than this by extend the diagram into this. Let's say I'm going to extend okay, this, you will get Does it look like a box now? I think so. Yeah. Okay. So if I do this, if I add this, I'm going to have this quantity is V mu. What is the SV mu? It's some other type of energy anyway. So and then you get this SP mu. If you add here in this direction, right? This quantity you will get this too, and so here you will get TPN. It just adds this and then adds this. You will get 0 here. And PV here and mu n here. You can play with this kind of thing and then you get new type of potential. But at the end here you get 0 because it's going to cancel it out, then you get 0. Okay. This is the diagram that we have. Okay. Next, I'm going to talk about Maxwell relation. which is telling us about the exactness, right? I give you the definition of the exactness in terms of mathematics in the very first lecture, right? And then you will see this again. Okay, suppose that we now consider the internal energy. You know that the chain Dn. And so as we derived earlier, and I'm going to put here again, okay. All right. So I'm going to call this as A. Okay. So from A, if you look at derivative with respect to the V, right, and then it means that U and S here, right, is interchangeable. So it means that you have this and you have here. This is the first equation. It means that it equivalent that if you take this is B, actually this is actually you take B, you will get right. Okay. Okay. Good. Okay. So again, but if I consider this instead, I going to have again I shuffle thing around. You will get Vn. Of course, that if I call this C, it means that this equation we get from C, right? And again, from A, oh no, from B actually. From B, if I look at N, you should actually do the C with this. This is the kind of equation that we could have, right, if this whole scheme, this whole scheme represents exactness, right, in that sense. And you can do the same for other types of potential energy. Thermodynamic potential, which is I'm going to leave it as a homework for you to do it yourself, because it's a lot. And then I just give you this very simple example. Right, you can try to do with this S or the Helmholtz or the Gibbs. Yeah, can do that. Anyway, so let me summarize a bit before we move to the next topic. So we experienced the concept of potential, right, before in the classical mechanics, right? At equilibrium, it is needed to be minimum, right? As I explain the situation of the chalk, right? If I leave the chalk, then it's going to fall down into the to the floor, because that the floor is have less potential energy, right? That is the preferred state of the chalk. So in this context, in this thermodynamic context, right? We are plenty of different type of potential, right? So it's very useful to computing at equilibrium. That involved chemical reaction, right? Or measuring the property of material that you consider in chemical reaction. With various condition for example, if you consider that your condition is to keep the pressure constant, right, or you keep your volume constant, or you keep your entropy to be constant, then it's kind of a choice that you can play with. Okay. Suppose the first situation, if your entropy and your volume of the closed system fixed, right? Yeah. The internal energy decrease and reach a minimum value at equilibrium, right? Because you know that we have this relation right here. But when the temperature and the volume are fixed, right, the Helmholtz decrease and of course you reach a minimum value at equilibrium. Okay, so by having these two conditions, again, you have this inequality right here. It means that it depends on your setup of experiment. That actually, if you want to keep these two variables fixed, it means that you can you can look at your system through this internal energy. But if you prefer to fix temperature and the volume, right, you can study your system through the Helmholtz energy, right? That is thing. And of course, then if you there are more actually. If you keep P and S are constant, then it means that the enthalpy will be decreased, and if you fix TP, all right, your Gibbs will be decreased somehow. Okay, so it means that you might have a question in your head that, oh, now we have so many types of thermodynamic potentials, right? And which one that we're going to use? Then you can use anything. It depends on your choice of setup or condition that you can use in the experiment, that it allows you to keep that which kind of which set of variable fixed. that kind of thing. Okay, I hope you get the point. So let me put table. Potential. Natural variable. The first one. Do I did something wrong here, maybe? Mu n let me see. I'm not sure what I put here. I'm not sure. So this is going to be set variable. We have and you have keeps this. Okay. So the variable are fixed in the process. Called natural variables of that potential. So the crucial point is that thermodynamics potential can be determined as a function of its natural variables or of the dynamic property of the system can be found by taking partial derivative of that potential with respect to its natural variable, and yeah, that might be all. That's enough. Okay. That is the thing that I'm going to say. So it means that it depends on your setup, which type of which set of variable that you need to fix, right? Once you choose, that means that if you choose to work with the Helmholtz variable, all the thermodynamic properties, like what you can do, you do the derivative with this Helmholtz function. You will get what do you get? I could not remember. Anyway, but you get a physical quantity out of that, right? That is the thing. Okay, then I would say this is the end of this topic. Next, I'm going to talk about classical gas. We still have an hour to go. Then let's talk about classical gas before we stop. Okay. The next topic is classical gas. Right. I mean, no quantum effect. We don't consider any quantum effect or behavior at all. We need only to consider the classical behavior of the gas, right? Okay. So actually, it's so normally, so you consider like a box that contain a lot a gas molecule or atom, a bunch of gas. Yeah, right here. Suppose. Okay, right. Okay. So what we're going to look at is at the macroscopic level, right? We to measure like these three quantities that actually is the thermodynamics quantity that need to, but this however associate with the motion of gas right here. So then, if we want to explore in more detail about the behavior of the gas, and then we need to, I'm going to give you first this number. Okay, so if I put a question, how many atoms in 1 mole? Okay, 1 mole is 12 grams. This is the definition of 1 mole anyway. So the answer is that we can determine experimentally that you're going to have, roughly speaking, this number. Okay, you should actually call avocado number. So it's nothing but a number of the atoms in 1 mole. Okay, which is quite a lot. So if we have n mole, if you have n moles and you ask how many atoms that you could have, right? You can say that, oh, okay, you have n atoms. So it means that, so 1 mole, you have Na, so this could give you this relation right here. Okay, next. To ideal gas. So can you give me what is the definition of the ideal gas? Can you? Okay, the ideal gas is not a real gas. Because it's called the ideal, right? Then it's not doesn't exist. Yeah. Because it's in your is ideal gas, right? It's mean the simplest somehow. The simplest system of gas, I would say. So when we want to study, when you say, okay, I want to study a macroscopic property of gas, which is I mean by these three quantities. The question, which gas? That is the thing. Hydrogen, oxygen, or which one? That is so well, you know that actually the molecular structure of each of these gas is totally different, right? Then it means that so what we want to make things simple. I mean, because physics is I mean, kind of lazy, where we want to do something simple first, and then leave the hardcore thing for students. Okay, all right. So if we define 1 mole sample of various gases in box of identical volume and temperature, then the measure pressure in P are almost the same at lower density Okay, this is the condition. If it's the density is very low, even though we have different type of gas in different box, the behavior is all more or less the same. That's the kind of thing. It means that somehow it's kind of less kind of interaction, or that because the interaction between the gases give us something different, right? It means that in very low interaction, it's very rare to happen. That is the reason why we get almost exactly the same pressure here. That is the thing. So the difference Okay, 10 to, I mean, the difference is been that actually coming from the interaction of each other. They will disappear. And you have this, your high school equation, right? Where this R is get constant, which is no. So if your gas behave according to this equation, you're going to call ideal gas. This is called ideal gas equation. Okay, that is the thing. So let me put a definition, because from this kind of message here, we can say that the definition of the ideal gas is a collection of identical particles in which interaction okay, that's it. Okay, we can simply put this as a definition of ideal gas. The even is not identical particle. I mean, they are very low. I mean, density is going to behave more or less like ideal gas, but not in that perfect, right? But approximately, yes. And then, so I believe that from your high school, you go, you do have this one, right? Okay, so if we look at, I'm not sure that I'm going to draw it beautifully, but I'm going to try. Yeah. Okay. And okay. And you also have this um, I'm quite sure that actually you have seen this surface before, right? This is a PVT surface, right? Yep. P is the surface. Okay. If you do a projection, so if you do a projection on this direction, you're going to have this going to P, and this is going to be T. So you're going to have this kind of curve, right? And then you will have this as a constant, this ratio between the volume and the temperature, right? But if you project on this side, here, you're going to have this curve, and of course this is V and T, right? And then, yep, PV, okay. And so the last bit is on this side. If you project this whole thing, right here, this is P, this is V, and then you will get this isotherm right here. Okay, you will have this. This is what we have for the, I mean, the classical gas. But there is a limit. Limitation. So ideal gas law does not work for low temp, high pressure, because at this condition, the interaction will play an im. Okay, so you cannot throw away the interaction in this situation, right? This is kind of a limitation of this formula, right? And so let me put more the assumption about the ideal gas. Okay. So the particles have no internal degree of freedom like rotation, vibration, so the point what we look at is just a point particle. Then you don't need to look at the rotation or the vibration, right? And of course, the second one, no quantum. That is a thing. No quantum. Now I'm going to introduce Boltzmann constant. Okay. And so it means that if you introduce this quantity, you are, your equation can be rewritten in terms of this Boltzmann constant. Okay, since we use the fact that here you use this relation, and then you will get this. Okay, so well, now if we keep the volume fixed and the temperature fixed as well, right? So it means that the quantity that we want to look at is a pressure, right? How this P relate to how does this P relate to the motion of the gas in the box, right? Because when the thing is that when we talk about this P, this is a macroscopic, right? But when you're talking about the motion, it somehow is kind of microscopic, right? Scale. Then so now we start to dig into detail that how this kind of micro behavior of the system give birth to this macroscopic property of the system. That what we're going to do next. Then okay, but I think I'll stop now. Is that okay? Because otherwise it's going to take yeah, because So next time we're going to look at the Maxwell distribution, or the kinetic energy of gas, actually. All right, and then after that, actually kinetic energy of gas, and then we're going to look at the real gas, right? Because now, today we're talking about the ideal gas. I hope you, well, this is kind of, you learn from your, I hope that you're actually high school, right? Okay.